In the last video, we considered two different functions, f of x, which is x squared minus 3x minus 2, and g of x, this more complicated looking function, x cubed minus 8x squared plus 13x plus 10 divided by x minus 5. And in both cases, we were interested in evaluating a limit, specifically the limit as x approaches 5 of the given function. And since I defined a limit as the height that the graph approaches when the x coordinate gets really close to that value, a naive way to evaluate a limit would just be to evaluate the function at that point. Consider f of 5, right? 5 squared minus 3 times 5 minus 2, 25 minus 15 minus 2, that's 8. The height of this graph when x equals 5 is equal to 8, so you might think that the limit as x approaches 5 of this function f of x must also be equal to 8. But I cautioned you against using that approach because even though it worked in this first example, it did not work in this second example where we tried plugging in 5 and we got an undefined output, 0 divided by 0. And that's all kind of confusing when you look at it algebraically, but once you get a look at the graphs, it's really obvious what's going on, right? In this first case, our graph is what's called continuous. So when your x value gets really close to 5, your y value is going to get really close to the height the graph takes on when x equals 5. But that's not the case down here where the graph is not continuous. As you likely figured out, this idea of a graph being continuous is super important for limits, and I'm throwing that word around without having ever defined it. So what I want to do in this video is talk more about what it means for a graph to be continuous versus discontinuous, and then focus on the more challenging cases where my graph is discontinuous and I'm trying to evaluate a limit. Because if my graph is continuous at a given point and I'm trying to evaluate a limit, it's really easy. We don't need to spend any more time on this specific case. So without further ado, what does it mean for a function to be continuous? Well, unfortunately, to give you the real definition of continuity, we're going to need to know more about limits. So we're kind of going around in circles here, right? Understanding continuity will help us understand limits, but before we can really define what it means to be continuous, we have to understand limits. So it's a little bit tricky. Maybe for now I can just give you an informal definition of what it means for a function to be continuous. Don't worry, we're going to do better than this later on. Informally, a function is continuous if you can graph it without picking up your pencil. I know that sounds really weird, but what I mean is in this graph here, if you were trying to draw it, you'd be totally fine drawing this part of the graph. You'd get over to here, and then at this point right here, you'd have to stop. Because that open circle is not part of your graph. You'd have to pick your pencil up and then put it back down on the other side of that open circle and draw the rest of your graph. You can't draw the entire thing without picking up your pencil, therefore the function is discontinuous. If you want to go back to our hiking analogy, imagine a hiker. Can the hiker hike from the start of this trail to the end? Well, it sure seems like it. The hiker's doing totally fine, comes around here, and then hits this point. And this open circle is not part of my graph, so the hiker falls through to his death somewhere down here. The hiker's unable to make it from the start to the finish, thus the graph is not continuous. We could talk about continuity on an interval. For example, I could say this graph is continuous from, -1 to +3, because I can sketch the portion of the graph from -1 up to +3 without ever picking up my pencil, no problem. But if we don't specify an interval, assumed when we talk about continuity is it has to be continuous on the entire domain. As you can see in this example, we're certainly not continuous at this point 5. So maybe you're thinking, okay, when you have these holes, your function is discontinuous. Well, that's true. When you have a hole, your function is certainly discontinuous at that point. In fact, it has a fancy name. It's what's called a removable discontinuity when you have a hole like this. But that's not the only type of discontinuity, as you see with the next example. Clearly, this graph shown in green is discontinuous, right? If you were trying to draw it, you could draw this part, but then you'd kind of get stuck. You'd have to pick up your pencil, start from the start up here, and draw this part. We have this discontinuity at -3. Think about the hiker if you want. The hiker is hiking down this super steep cliff infinitely far. There's no way for the hiker to get from the start of the trail to the end of the trail without teleporting from the bottom here up to the top here. Here's an example of what's called an asymptotic discontinuity. It's worth pointing out that I'm just giving you examples of these two different types. Every removable discontinuity won't look identical to this, and every asymptotic discontinuity won't look identical to this, but hopefully they'll be close enough that you can tell the difference. Let's see, let me try to come up with a slightly different looking removable discontinuity. Here's a function and everything appears to be going fine, and then I have this open circle, this hole, and that's the key to a removable discontinuity. In this case, the function is undefined at 5. The function doesn't have to be undefined at 5, it just can't be defined at that point. So what I'm saying is I could put a closed circle, right here if I felt like it. It doesn't matter. This is still discontinuous at whatever this x value is, maybe 1 in this case. Because again, you couldn't draw the entire thing without picking up your pencil. A hiker couldn't get from here to here without falling through the ice here and getting stuck in this crevasse. The asymptotic discontinuity that's shown in green here has kind of opposite behavior on either sides of the vertical asymptote. That doesn't necessarily have to be the case. Here's another function that has an asymptotic discontinuity. This time the vertical asymptote appears to be at -2 here. To the left of the vertical asymptote, we go up towards infinity. To the right, we go up towards infinity. But because these lines never connect, I can't sketch the graph without jumping from here over to here. A hiker could not get from my start over here on the left to the end over here on the right. Here's another picture of an asymptotic discontinuity. The third type of discontinuity is what's called a jump discontinuity. And I guess the name kind of makes sense. You're sketching your graph totally fine, everything's going smoothly until you get to this point. And then the height jumps from -3 down here to -5, and then the graph continues again. Clearly we're discontinuous, but it's a slightly different kind of discontinuity than we saw here, where the hiker would just have to climb over this little gap in the trail. In this case, the trail starts back up at a different spot than where it left off. It's not super important that you can tell the difference between these three different types of discontinuities. In fact, I think if I really got clever, I could come up with an example that wouldn't really fit any of the three, right? Like I could draw some function that has this vertical asymptote on one side and then maybe has an open circle here and heads out this way. Would you call this a jump discontinuity or an asymptotic discontinuity? I don't know, it kind of has features of both, right? It's asymptotic on one side, but on the other side, it doesn't really have an asymptote. If I was forced to classify this, I might think of it as an asymptotic discontinuity, but frankly, I'm not sure which type it would be called technically. But the good news is we don't care. I just want you to understand that not all discontinuities look like this example that we saw here. A function is discontinuous if you cannot draw the entire thing without picking up your pencil. You cannot get from the start to the end if you're a hiker by walking along that line. And even if that feels a little bit informal for a math class, I think that level of understanding will serve you really well as we continue to explore discontinuities. So you're like, okay, I kind of understand what a discontinuity looks like. The whole purpose of this section is understanding limits. What can I do with limits when I have a discontinuity, right? If my function is continuous at a given point, like x equals c, then it's really easy to evaluate the limit as x approaches that point. All we have to do is put that point into the machine. This is the example that we saw at the start of the previous video, right? We were evaluating the limit at a point of continuity. Because my function was continuous at that point, the limit as I approached that point was the exact same as the height of the function at that point. But what if that's not the case? How do you evaluate limits at points of discontinuity? Well, a good place to start is looking at what are called one-sided limits. The notation for those are pretty similar to the notation we'd already seen. We write LIM to denote the limit, and then we write an X and an arrow to talk about X getting close to some point. 5 is the point that I'm interested in this specific example. But I'm not just going to say the limit as X approaches 5. I want to know about the limit as X approaches 5 from the left side. The way I denote that I'm coming from the left side is I put a little negative sign up here in the superscript. So the way you read this is the limit as X approaches 5 from the negative side of this function f of x. The way you're thinking about it is you're a hiker and you're getting really, really close to 5, but you're not exactly on 5 because you can't be on 5 because it's not part of the graph. And you're like, oh, okay, are you just short of 5 or are you just past 5? Are you the purple hiker or are you the green hiker? Well, if we're approaching from the left side, we're walking in this direction, we're the purple hiker. If we're approaching from the right side, we're the green hiker, and what that notation would look like is really similar. We'd write the limit as x approaches 5, but now since we're coming from the right side, aka the positive side, we put a little plus up here in the superscript. The question in purple is asking, if you're walking this way along the path, what height do you approach as your x value gets really close to 5? The answer to that question is 8, because this person in purple is getting really close to a height of 8. The question in green is asking what height do you get really close to if you're walking along this trail, but you kind of start at the end and are walking backwards. You start from the positive side. If you're thinking about your x values here, positive numbers are on this side, negative numbers are over on this side. We're starting from this side and walking in this direction. We're walking downhill. Well, this green hiker is walking downhill, and as the green hiker gets close to 5, he's also getting really close to a height of 8. So in this case, both of the one-sided limits give you the same answer, 8. When you're in that case, that each of the two one-sided limits give you the exact same answer, then that defines the two-sided limit. The the limit as x approaches 5, with no plus or minus written right here, of f of x is always going to be undefined unless the two one-sided limits give you the same answer. And in that case where the two one-sided limits give you the same answer, that answer is what the limit is equal to. What I'm saying is because I got an 8 here and an 8 here, this is an 8. However, if you compare that to this case over here, the limit as x approaches 2 from the negative side is talking about the height of this hiker somewhere over here, which appears to be getting really, really close to -3. But the limit as x approaches 2 from the positive side is talking about the hiker who's coming in on this direction, and when this hiker gets really close to an x value of 2, he's standing way down here. He's getting close to a height of -5. Over here, the two one-sided limits agreed, so that defined their two-sided limit. Over here, the two one-sided limits do not agree. You get different numbers here. -3 is not the same as -5. So what that means for the two-sided limit is it's undefined. Two-sided limits are always undefined unless the two one-sided limits give you the exact same answer. You may be able to generalize at this point. You might, if you're really good at these, be like, wait, anytime you have a removable discontinuity, aka a hole, the height of the graph is going to be approaching the same value to the left or right of the hole. That's kind of the defining characteristic of a removable discontinuity. We just took 1 point out of the graph. Yep, that's entirely true. Anytime you have a removable discontinuity, the two one-sided limits are going to agree, so you're going to be able to have a two-sided limit. However, anytime you have a jump discontinuity, that means the height on one side of the discontinuity is different than the height on the other side of the discontinuity, which is going to make the two one-sided limits produce different values. Therefore, the two-sided limits are always going to be undefined. What about the asymptotic discontinuity? Well, we can kind of do the same analysis. In this case, our discontinuity is at -3, so we might be interested in the limit as x approaches -3 from the negative side of f of x. That's asking ourselves the question, what height is this little hiker over here going to get really close to when he gets arbitrarily close to an x value of -3? Well, this graph continues down infinitely far, so this height is going to be an infinitely large negative number. In other words, the limit as x approaches -3 from the negative side of this function is -infinity. You could probably already see what's going to happen to the hiker on the other side of the -3. The limit as x approaches -3 from the positive side of f of x is going to be equal to +infinity. And that's because this graph goes infinitely high as it gets closer and closer to -3. Do the two one-sided limits agree? Nah, they couldn't be more different, right? -infinity and +infinity. Therefore, the two-sided limit does not exist. Generalizing this result is a little bit more complicated. In this case, the two-sided limit did not exist, but that's not always the case. It's possible to have an asymptotic discontinuity where the limit does exist. And here's an example of such a case. The limit as this graph approaches -2 from the left side is +infinity, and the limit as x approaches -2 from the right side is +infinity. Therefore, in this specific case, the limit as x approaches -2, the two-sided limit, is equal to +infinity. So sometimes when we have asymptotic discontinuities, the limit does exist, but sometimes when we have asymptotic discontinuities, the limit does not exist. To see if that all made sense, consider this example here. There's lots of different points we could pick on, but I think if you can figure out these 4 questions, that shows really good understanding of one-sided limits. So first, the limit as x approaches 4 from the positive side of f of x. If you're thinking about the hiker standing over here, that's perfect. What height is this person getting really close to? When the x value gets really, really close to +4, it looks like that's a height of -1. Contrast that with the hiker who's approaching 4 from the negative side. So now we're thinking about this hiker over here. What height is he or she getting really close to when we get close to 4? Well, whatever height this is equal to, it looks to me to be -7. What if there was no plus or minus here? Well, then I'm asking you about the two-sided limit. Oh, right, two-sided limits. What was that again? Two-sided limits are the easiest if you've already figured out the two one-sided limits. If you see the same number here and here, that's your answer down here. If you see a different number here and here, then your answer down here is that the limit is undefined. It's easy to learn new topics and kind of forget stuff that you already know. So I want to make sure that doesn't happen by asking question D here, which kind of doesn't look like the others. This is just asking you what's f of 4. This has nothing to do with limits at all. This is just asking you if you put 4 into this machine, what would come out? You come over here to 4 and you look for the closed circle that in this case appears to be -7, and that's what comes out of the machine. It ends up being the same as the limit as x approaches 4 from the negative side, but really it doesn't have to. When we're talking about limits, especially at points of discontinuity, we're not concerned with the output of the function at that point. So while f of 4 is equal to -7, that's not really relevant. Our analysis is just concerned with a, b, and c up here. For most students, limits come pretty quickly to them, especially when you're given a graph. Where things get a little bit more challenging is when you try to conquer limits algebraically. What if you didn't have the graph? What if you just had an equation? Could you figure out some one-sided limits? Well, let's see. Here's 2 algebraic examples for you, and I'm not providing you with the graph. Maybe at the end I'll sketch the graph of these 2 functions for you so you can confirm what your answers are. But for now, I want you to try to tackle these completely algebraically. So what's going on in this first one? We're taking the limit as x approaches 10 from the positive side. So in your head, you're picturing the hiker who starts out greater than 10 and is walking down towards 10, but always is ahead of 10. So if it helps in your head, you can think 10.0001 or something like that, if that helps you to understand what this means when we talk about the limit as x approaches 10 from the positive side. We're thinking about an x value slightly more than 10. If you take a number slightly more than 10 and put that in for x here, what happens? Well, slightly more than 10 minus 10 gives me a number that's damn near 0. It would be a slightly positive number because this is slightly bigger than 10. So I have a slightly positive number, and when I take the absolute value of a positive number, the absolute value symbol doesn't do anything at all. So up top I have a number that's almost 0 but slightly positive. But things get kind of complicated when you look at the denominator, because in the denominator, if I again take a number that's slightly bigger than 10 and plug it in here, and then subtract 10, I'm in that same case where I have a very slightly positive number. In fact, the number that I have up on the top is the exact same as the number that I have down on the bottom. When you have a fraction and the top of the fraction is the exact same as the bottom of the fraction, the value of that fraction is just equal to 1. And you're like, yeah, of course, that's obvious. This is the same as this. Anytime I divide something by itself, 1 is what comes out, so this limit must be equal to 1. Well, it's not as obvious as you might think. If we call this function, I don't know, h of x maybe, the absolute value of x minus 10 divided by x minus 10, and then we evaluate this function at 10 itself, we're not going to get 1. Because when I put 10 into this machine, 10 minus 10 is 0, the absolute value of 0 is 0, and 10 minus 10 is again 0, so I get 0 divided by 0, which is undefined. So we're again at one of those cases where what's going on here is this function is discontinuous at 10. However, as long as our value of x is greater than 10, the absolute value symbols don't do anything at all because we have a positive number up top. The x minus 10 and the x minus 10 cancel out, and I'm left with just 1. What if we looked at the other one-sided limit? What if we looked at the limit as x approaches 10 from the negative side of this same expression? You might want to pause and see if you can figure out what this limit would be equal to. It's not obvious at all. If x is a little bit less than 10, maybe in your head you're thinking 9.99999 or something like that. If we have a little bit less than 10 and we subtract 10, we're very close to 0, but we're slightly negative, right? If I have less than $10 and I have to pay somebody $10, I don't have enough to pay them off. I'm in the negative here. A number like 9.99999 minus 10 is negative. And that's really important because if this is negative, what the absolute value symbols do is they change the sign of that number. And now the top of the fraction is no longer the same as the bottom of the fraction. The top of the fraction is a number really close to 0, but positive because of the absolute value symbols. The bottom of the fraction is that same number really close to 0, except that it's negative because our value of x is less than 10. So we have a number divided by a number. The magnitude of those two numbers is the exact same, but one of them is negative and one of them is positive. When you have a negative divided by a positive, you get a negative number. This limit is equal to -1. The limit as x approaches 10 from the positive side is +1. The limit as x approaches 10 from the negative side is -1. Therefore, the limit as x approaches 10, the two-sided limit of this expression, x minus 10 absolute value divided by x minus 10, does not exist. If you want to test yourself on these one-sided limits algebraically, maybe try this problem on your own. It's almost identical to what we did up here. What is the limit as x approaches pi from the negative side of the absolute value of sine of x divided by sine of x? Well, maybe you remember that the graph of sine looks something like this, where pi is this value. If we're putting in a number slightly less than pi, we're thinking about the hiker that is standing just over here, just to the left of this x value of pi. What I'm saying is that when x is slightly less than pi, the sign of x is close to 0 but slightly positive. Because it's positive, the absolute value symbols don't do anything at all, and that slightly positive number that we get here is the exact same as the slightly positive number that we get here. Therefore, this limit is equal to positive 1. You might be able to see the punchline already. If we took the limit as x approached pi from the positive side, now we're thinking about taking values of x that are slightly bigger than pi and putting them into this sine function. When our value of x is slightly bigger than pi, the height, the output, is slightly negative. It's getting really close to 0, but it's slightly negative. If sine of x is slightly negative, the denominator is negative, but the absolute value up in the numerator makes that positive. I again have something with the same magnitude on the top and the bottom. However, one of those things, namely the top, is positive, and the other one, the bottom, is negative. When I divide a positive by a negative, I get a negative number. The limit as x approaches pi from the positive side is equal to -1. We again have different one-sided limits, therefore the two-sided limit does not exist. I hope I didn't confuse you too much by drawing this graph. This graph is not the absolute value of sine of x divided by sine of x. This graph is just y equals sine of x. This was just to try to help you understand what comes out of the sine of x machine when we put values close to pi into it. And then from that, we can do the analysis on this function. The graph of the absolute value of sine of x divided by sine of x does not look like this. In fact, what it looks like, close to pi anyways, is something like this. As long as my value of x is slightly less than pi, so here you're thinking about the green hiker, the sine of x is positive, so the absolute value symbol isn't doing anything at all. I have something divided by itself. When you have a fraction and the top and the bottom of that fraction are identical, the value of that fraction is equal to 1, which is why the height over here is all 1. At pi itself, sine of x equals 0. The absolute value of 0 is 0. Sine of x is 0. I get 0 divided by 0. I get something that's undefined, which is why I have no height associated with this graph at pi. When my value of x is slightly greater than pi, so now I'm thinking about the blue hiker over here, what comes out of the sine function is negative. The absolute value makes it positive. I get positive divided by negative, so I get -1. Pictured over here in brown is the graph of y equals the absolute value of sine of x divided by sine of x, at least a portion of the graph. And using that portion of the graph, we can confirm the answers that we got for our different one-sided limits. I think I promised you a picture of this graph as well. Turns out it looks almost identical to this. The only difference is we don't switch from +1 to -1 at pi, and the other values where sine equals 0. We switch from +1 to -1 at 10. The graph looks something like this. When I'm approaching my discontinuity at 10 from the right side, in other words, when x is slightly greater than 10, the height is equal to 1. Maybe I'll do that in blue for the sake of color coordination. And when I approach 10 from the left side, the height's at -1. In both of these algebraic examples, I had a jump discontinuity. And when I have a jump discontinuity, the two-sided limit ends up being undefined. For most people, the graphing part of these one-sided limits is fairly straightforward. Most people are able to follow this example pretty well. But when you get to these algebraic examples, it gets really hard. Okay, I'd prefer that you don't do things this way. But if you really get lost in evaluating these algebraic one-sided limits, if you have a really hard time figuring out this blue box and this green box, there's a way to cheat. Technically, you shouldn't do this, and I feel a little bit guilty even telling you, but it'll always work for our purposes. You can take a value of x that's slightly bigger than 10, like 10.001, and just plug that in here. 10.0001, I guess, minus 10 is 0.001. The absolute value of 0.001 is 0.001. So if I plug in 10.001, the top of this fraction becomes 0.0001. And then if I plug in 10.0001 to the bottom of this fraction, where I subtract 10, the bottom of the fraction becomes 0.001. And if I pull out a calculator and take this number divided by this number, what you'll see, what comes out is exactly 1, which is the limit that we got right here. I'd prefer you don't do this by plugging in numbers like this. It's better to have a general understanding of, as long as x is slightly greater than 10, here's what would happen. But if you really struggle with this, that will get you the answer. Similarly, if you really struggle getting this -1 right here, take 9.9999 or some other number that's really close to 10 but slightly less and plug that into this function. 9.9999 minus 10, pull out a calculator if you need to, is -0.0001. So the top of my fraction is the absolute value of that negative number. The bottom of my fraction, if I take this same 9.9999 and subtract 10, will be -0.0001. If you take the absolute value of this negative number, it becomes positive. So it becomes positive 0.0001, whereas the bottom is still -0.0001. And if you take a calculator and divide these two numbers, you'll see -1 is what comes out. You can get these limits by plugging in numbers, but I'd prefer if you don't actually plug in the numbers and instead just sort of think about the behavior as our value is slightly less than 10. I think that'll serve you better going forward. We'll do more with these algebraic examples in the next video because there's some pretty tricky cases we need to consider, but this video is getting pretty long, so I think I want to end it right here.